In this statistics lesson, we will be discussing hypothesis testing for proportions. We have only one objective, and that is how to use the z-test to test population proportions. Just a reminder that to find a sample proportion, you just need to find the number of data points that are successes divided by the total number of trials in your binomial experiment. So just a reminder from previous lessons. All right, so when we are doing the z-test for a population proportion, that's the good news, there's only one, and it is the z. This can be used when a binomial distribution is given and these two things must be met. The n times your p must be greater than or equal to 5, and your n times your q must be also greater than 5. So make sure that you test that, make sure that you have those qualifications before you get started. All right, the test statistic in this will be the sample proportion, which is p hat, and the standardized test statistic that we will be using is the z, and the z in this case is p hat minus p, so it's this right here, p hat minus p, and then you're going to divide that by the square root of p times q over n. Very important that you don't get p and p hat mixed up in these problems, so just note of caution, make sure that you're being very consistent with your labeling so that you don't get those confused, your p hat and your p, and your q hat and your q, very important. All right, here are the steps. So again, if you need to, take a moment, write them down. They should look oddly familiar because they look almost exactly like the ones we were doing for mean. So there's not much of a difference. It's just the biggest difference is that test statistic, really. So that's the nice thing. Okay, so here we go. Let's just jump right in and do some examples. All right, a researcher claims that for less than 69%, of U.S. adults who use live television streaming platforms have upgraded to advertisement-free service tiers. Okay, so that's the claim. So let's write that down. So the claim is that the proportion is less than 0.69. Again, remember, if you're talking about percentages, make sure you use decimals. All right, and that is my alternate, because notice there's no equal. So my null would be that p is greater than or equal to 0.69. All right, notice my alternate is less than, so this is going to be a one tail, a left tail, in fact. So it's going to be that, and we're going to have a left tail over here. Okay, so I'll just color that in. Okay. Next up, it says in a random sample of 100 adults, so my n equals 100. All right, and I already know that my p equals 0.69, which means my q must be 0.31. So I'm going to write those down right now because I already know them given the problem before. All right, so it says in a random sample of 100 U.S. adults, 65%. So my p hat is 65%, and my q hat would be 35. Now the good news is you don't need q hat for this problem, but it's always nice to have it there. So that would be your point estimate for the failures. At alpha equals 0.01. All right, we need to test, is there enough evidence to support this researcher's claim? So my rejection region will be this 0.01 right here. I will need to find my critical value, my z critical value that goes there. So I go into my chart and I look for that 0.01 area, and that z-score is negative 2.33. So there's my critical cutoff for my rejection region versus my non-rejection region. All right, now all I need to do is find the test z, and I should be good to go, and we're going to see where that falls. All right, so the test z, remember, is p hat minus p divided by the square root of p q divided by n. All right, so your p hat is 0.65 minus your p, which is 0.69, and then you're going to divide that by the square root of 0.69 times 0.31 divided by 100. And that all that in the denominator is under that square root. So when I plug that in my calculator, I get that is approximately negative 0.86. And that is above, right? Definitely above. So it's going to fall right there. So that's definitely in the do not reject. So we're going to fail to reject because we are not falling in that rejection zone. So when you put it in words, I'm going to fail to reject the null. So I don't have enough evidence to say that's wrong. So my claim is unfortunately not good. So there is not enough evidence to support the claim that there is the less than 69% of adults use live television streaming platforms that have upgraded to advertisement-free service tiers. Sadly. I know I haven't. I still get ads on mine because it's cheaper. All right, let's try another one. A researcher claims that 26% of U.S. adults between the ages of 22 and 59 who do not have a parent with a bachelor's degree have completed a bachelor's degree themselves. All right, so there's my claim. So let's start there. So my claim is that 26%, so my proportion is equal to 26%. Doesn't say less than or greater than, so that's definitely my null. My alternate is then going to be p is not equal to 0.26. All right, so this is definitely going to be a two-tailed test. So I'm going to come over here and sketch my picture. Two tails. There we go. So there are my rejection regions. All right, let's read some more. In a random sample of 7,400 people, so there's my N. Oh, and I should stop and do my P and my Q here. So my P is 0.26, which means my Q is 0.74, right? Those have to add up to 1. All right, my N is 7,400. It says 1,984 say that they have completed the bachelor's degree themselves. So my P hat is going to be 1984 divided by 7,400. And that comes out to about 0.268. And my advice is this. When you do this, either go out a bunch of decimal places, like go 2 or 3, at least 3, or just use the actual fraction when you do the computations. The more accurate you can be, the better off, the closer your test statistic is going to be, as if you were using technology. So the more accurate you can be the whole time, the better off you are. All right, so there's your p hat. All right, so we are at an alpha of what? Alpha of 0.10. So that means we have 0.5% here and 0.5% here. So that critical value, that z critical value on both of these, remember, same number, but one's going to be positive and one's going to be negative, should be 1.645. So positive and negative 1.645. Okay, so there are our critical regions nicely set out and ready to go. Okay, so now all we have left to do is find that test z and see where it falls, and then we can make our conclusion. All right, so the test z, again, p hat minus p over the square root of pq divided by n. So p hat is 0.268 minus 0.26, which is our p, and then divided by the square root of our p, which is 0.26, times our q, which is 0.74, and that would be divided by 7,400. Okay, and remember, all that is under the radical in that denominator. So my test, when I put that on my calculator, that turns out to be about 1.59. So this, where does the 1.59 fall? It doesn't quite fall there, so it's going to be right about there. So that means we fail to reject, right? Because we are in the fail to reject zone. So fail to reject the null hypothesis. So then let's go back and take a look. So our null was our claim. So we cannot reject that. So it looks good for us. So there's not enough evidence to reject the claim that 26% of U.S. adults ages 22 to 59 who do not have a parent with a bachelor's degree have completed the bachelor's degree themselves. Pretty cool. So that is that test result from beginning to end. All right, next example. A study of sleepwalking, it's now called nocturnal wandering. I guess we have to be PC about even sleepwalking these days, was described in Neurology magazine. And it included information that 29.2% of the 19,136 adult Americans have sleepwalked. Would a reporter be justified in stating that fewer than 30% of adults have sleepwalked? let's use a 0.05 significance level to test the claim. That for the adult population, the proportion of those who sleepwalked is less than 0.03. Okay, so let's 0.30. Okay, so I'm trying to change the color. There we go. All right, so let's start by writing down all of our information. All right, so our sample looks like it's random. I don't see, especially if it's in a neurology magazine, that's probably pretty good. We have a fixed number of trials, right? They're all independent because I know that's going to be a good thing. And that number of trials is 19,136. All right, I should double check to meet the requirements. Make sure that your N times your P, and again, your P in this case is going to be that 30%, so 0.30, which means your Q is going to be 0.70. So make sure that your N times your P and your N times your Q are both greater than 5, which of course they will be with a sample size this huge. So I'm not going to even multiply those. All right, so let's talk about their claim. What is the claim? The claim is that the proportion of those who sleptwalk is less than 30%. So the claim is that the proportion is less than 0.30. Okay, so that is our alternate because it doesn't have an equal sign. So our null is going to be that P is greater than or equal to 0.30. So this is going to be a one-sided. It's going to be a right wing, right? A right there. Okay, so there is our rejection zone over here. All right, let me see. Okay, so we got that. Okay. So our significance level, there we go. I was like, what am I missing? My significance level is 0.05. So there's our significance level. And I can now start looking at either, using your technology. You can use whatever you would like. At this point, if you would like to use the p-value, again, I caution you, p-values really lend themselves to using technology. But because this is a z, we can actually find this ourselves too. So let's do the p-value method on this one, and then we can check it using technology. All right, so if we're going to use the p-value method, remember this is going to be your p-value. P-value is going to be right there. And then this is going to be our test statistic. All right, our test z. So that's the next thing we need to find is that test z. All right, so the test z, remember, is p hat minus p over the square root of pq divided by n. So p hat in this case, okay, so we're going to, our p hat, where was that? Oh, it's right here. I didn't write that down. P hat is 29.2%. So the p hat, so I'm going to go back here, p hat is 0.292. So 0.292 minus the p, which is 0.30, and divide that by the square root of p times q divided by n, which is 19,136. Okay, so I'm going to put all that in my calculator, and let's see what I get. All right, so I put all that in my calculator, and I get about negative 2.41. So there's my test z right there, negative 2.41. All right, so if I go to my z chart and I look up an area, the z-score of negative 2.41, negative 2.41, let me get my chart out. All right, that gives me an area. So this area, my p-value is 0.0080. All right, so my p-value is 0.0080. How does that compare to my alpha, which is 0.05? That p-value is much smaller. So if the p is low, the null must go. So I am going to I'm going to reject my null. Okay, so I'm going to reject my null, which is not my claim. So that's nice for me because I'm not rejecting my claim. So that means that we are in support of that alternate hypothesis. So there is sufficient evidence to support the claim, our claim, that fewer than 30% of adults have sleepwalked. Right. The good news with this is everything worked out nicely. Really, the only time, if you're doing p-values, that you might want to make sure that you use technology is when you are doing t-distributions. Z's, it lends itself very nicely to, but t's, not so much. So I would definitely take that into consideration if you are doing a t-distribution, that maybe using the p-value method isn't the best way to go about things. All right, and one more example, medical leave. The Family and Medical Leave Act provides job protection and unpaid time off from work for a serious illness or birth of a child. In 2000, 60% of respondents of a survey stated that it's very easy to get time off. If a researcher wishes to see the percentage who said that it was very easy to get time off has changed, they sampled. Okay, so let's back up a little bit. All right, so in 2000, 60% of respondents. Okay, so that is and 60% said it was easy to get time off. So there's my claim. So we're trying to figure out, has it changed? So the claim is that it's still P equals 60%. And that is my null hypothesis. So my alternate hypothesis would be that P is not 0.6. All right, so this is going to be a two-tailed event. So let me draw my picture. Two tails. There we go. Okay, a researcher wishes to see if the percentage has changed. Okay, so he's going to do a sample. All right, so I should probably list out my P. My P is 0.6, which means my Q is going to be 0.4. So I'll list that out. So the sample was of 100 people, and my P hat was 0.53 when I looked at that sample of 100 people. And we want an alpha of 0.01. All right, so if your alpha is 0.01, let's see, should we use the p-value or is this a critical value method? Let's do the critical value method this time. I guess it really doesn't matter which one we do, but let's do the critical value this time. All right, so since alpha is 0.01, that means this is 0.5%, so 0.005, and this is also 0.005. So this critical value here, this C critical value, again, remember these are going to be identical. One's going to be positive, one's going to be negative. That one's going to be positive. I'd go to my chart and I'd look up that area, and that turns out to be, when I look at my chart, you know, I think we've done two that are critical value. We've done critical values already. You know what? Let's erase this and let's do the p-value method, because I think we need to see another p-value method. I want to make sure I do more than one example. So let me try this again. Sometimes I think out loud when I'm doing these problems and I forget what I'm supposed to be doing. All right, so alpha equals 0.01. Okay, so p-value method. All right, so we need to find the test value and then go from there and then help us find our p-value. Remember the p-value, these are going to be identical, right? So p-value is going to be two times this area. So I'm going to write that below it. P-value is going to be 2 times that area. And then we're going to compare it to alpha, which is 0.01. Okay, so let's get that test statistic out there right away. So z equals, again, p hat minus p over the square root of pqn divided by n. So our p hat is 0.53 minus our p, which is 0.6, and divide it by the square root of p, which is 0.6, times q, which is 0.4, divided by 100, right? And that's all under that radical in the denominator. So that turns out to be negative 1.43. So negative 1.43 is here, positive 1.43 is here. I'm going to look up the left one because that's definitely easier. When I look up this area right here, that area turns out to be 0.0764. So take twice that, and that turns out to be 0.1528. So that is definitely much larger than our alpha. And because the p is much larger, that means we fail to reject, right? So we're going to fail to reject our null hypothesis. So, and that was our claim. So we can't reject this. So that's good news for us. So that just means that there is not enough evidence to support the claim that the percentage has changed, right? Okay. Our claim is that it's still 60%, so there is not enough evidence to support that any change has happened. So still looks like it's 60%, unfortunately. And again, I could have done this using critical values. I just wanted to make sure I showed you another example where we're using those p-values. I was going to do the critical region initially, but then I changed my mind. So remember, you can use either method. So make sure you know how to do both critical value method and p-value method because you will be assessed on both. So thank you so much for listening, and we'll see you next time. Have a good one.